Okay, good morning, friends. So, in the last video, we discussed about a multiplier using a data path and control path. So, in this video, we are going to design a simple microprocessor, which name is MIPS 32, MIPS 32. It's a simple microprocessor used to carry out simple computations like addition of numbers, factorial. Okay, so here you can see the pipeline diagram of MIPS 32, which is represents its internal architecture. So there are mainly five stages. You can see that. First stage is called instruction fetch. Second stage is called instruction decode. Third stage is called execute. Fourth stage is memory access. And last stage is write back. So this diagram is the pipelined version of MIPS 32. Pipelined means uh, multiple instructions occur in a single clock cycle. Okay. The processor does not wait for a single instructions to complete. Instead, it execute one and the other all instructions one after the other without any lag. Okay. So this MIPS 32 processor. So what do we generally write? We give instructions in an assembly language program, right? And the assembly language program, the assembler converts the our input instruction into corresponding binary or machine code. So this MIPS 32 works on 32-bit instruction set. So the each program you type, where it's be add r0 comma r1 comma r2, or any program you type, it is going to convert into a 32-bit value, 32-bit machine code. Okay. So mainly MIPS 32, there are many instructions or many operations you can carry out. They are mainly they are mainly divided into register to register type, register to memory type, load and store type, branch type, and finally halt. So register to register type, you have instructions like add r0 comma r1 comma r2, add r0 comma r2 comma r3. That means two values are stored in registers, and the final value is also stored back in a register. That is called register to register type. So the second type is register to memory type. It means you are giving an immediate value instead of one register, like add r0 comma r1 comma 22. That means r0 equal to r1 plus 22. 22 here is a immediate value. Okay. Then third one is load and store. You can see that you want to load a digit from a memory, or you want to store a digit in memory, you use load and store instruction. And use jump instruction or branch instruction, which is used in the case of loops, where you need to find a factorial, you use branch instruction. And finally halt instruction is to end the process, right? So you can see that this architecture means register, you can see. Okay, these are the instructions. See, add rd comma rs comma rt, that is a register to register instruction. You see, you add two registers and store the register in another, store the value in another register. See, rs represents the source register, rt is the another source register, rd is the destination register. See, this is an rm operation, that means register to memory operation. Why? There is an immediate value. This is not a register, this is a immediate value. Okay. Okay, that's the case. So we can go to the code. Here you have here two test benches. One test bench contains the code for adding two registers or carrying out a register to register operation, and second one we are going to calculate an factorial of a number. So we can see the code of the processor. See, first I declare a MIMS 32, and you have two inputs here, two clocks, clock 1 and clock 2. There is a PC, that is a program counter. There is a program counter. There are various instruction registers, execution registers, memory registers, and many more, which all are 32-bit. Why? Because MIMS 32 is a 32-bit processing processor. Okay, you have a condition checker, you have a halted condition. Here you have a register is 32-bit 32 register. You have a memory of 32-bit 1 kilobyte 32-bit memory. Okay, you assign operations a binary value. See, uh, when you take the case of an instruction, this would be the like, see, an instruction which is a 32-bit. First 6 bits represent its type of instruction to be carried out. That is declared here, first 6 bits. If first 6 bits is full zero, then the operation is an addition. If this corresponds to this value, then it's a subtraction. If this corresponds to this value, then this is an branch equal to zero. Okay, this is a branch equal to zero condition, whole condition. So first 6 bits of that instruction, that out of 32 bits, first 6 bits corresponds to opcode. So the corresponding opcode, you have corresponding instructions here, and next 6 bits corresponds to its destination register, and next one corresponds to its operation or source register, and next one can be a another source register if it is RR type, or an immediate value depending on the type of instruction. Okay, so always at close call, if halted equals zero, halted means we stop or we end the process. If halted equal to zero, and if this is a branch condition, you make the taken branch equal to one, so that the loop is executed, and the taken branch condition is given here, so that this is a pipelined version. You know that multiple instruction take place at the same clock cycle. So if it's a branch condition, you don't want the next instruction to be executed until the branch condition is over. So you make taken branch equal to zero, which in the later case you can see that if taken branch equal to zero, only some instructions like store in the memory or write back instruction take place, right? Okay, so you give C type of instructions, you assign three values: RR type, register type, register memory type, loads type, store type, branch type, and hold type. And here you as look at the clock too. If this A register equal to zero, then you have execute A equal to zero. If A register is not zero, then you fetch the value 21 to 26 represents the destination register. No, yeah, represents the destination register. So you take the destination register. See, you take the destination register and you store in this register. Similarly, you take the source register and store in B register. Okay, and you take the immediate register and stored in this register. Okay, and you determine what type of opcode and instruction, and you type and you store that in execution type register. Okay, these all are registers of 32-bit, right? Then what you know, then you have the execution stage, in which you look what type of opcode is common. If this is opcode, then you add A plus B, subtract or A plus B, or it's a registered memory ALU type, then you add A plus that immediate value, and you do all this. If a load and store, what do you do? Then the memory location is given as A plus immediate value. You store in that ALU out register. If a branch instruction, you need to calculate the next instruction to be executed, and you stored in this value. Okay, and you have final stage, memory access stage or memory stage. In that you do memory write back or memory read. Okay, you do all these things. Okay, so this is the code of our processor. Then we can execute an program which add to value. Okay, you can look its test bench. See, We declare module test, we call clock 1 and clock 2, and you can see here, see, I initially set program counter to 0 so that the instructions are fetched from memory address 0. See, these are corresponding values corresponding to what? Corresponding to the 32-bit instruction set which I declare. Okay, so this is a simple instruction to add two numbers. So we can see, we can execute this. See, initially R0 is loaded with the 0, R1 is loaded with the 10, R2 is loaded with the 20, R3 is loaded with the 25. And in R4 you have what? R1 plus R2 30, and in R5 you have R1 plus R2 plus R3, that is 55. That was that program. And in the second program, you can see this is a program to find the factorial of a number, and the number here is given at 200 location 7. Okay, so we can execute that program. 2.a. Okay, see, we have given the number as 7 and its output is stored in memory location 198. 7 factorial 5040. Can do for another number like let's give a simple number like 4, right? You save that. See, 4 factorial given here as 24, that is 4 into 3 is 12, 12 into 2 is 24. Yeah, you get the 4 factorial in this memory location. So this way you execute the code for a pipeline processor and you write various programs to check whether your microprocessor works perfectly. So in this video description I'm gonna paste a course link which I referred. So I recommend you to at least watch the last two videos of that course that discuss this processor there and how operations or assembly opcodes are written. All that stuff are discussed in that course in the last two videos. So I recommend everyone to watch that last two videos of that course. That course was conducted by an IIT Kharagpur. So thank you.